Here is a combined summary of the two pages. LivePose is a novel method for online 3D reconstruction from monocular video with dynamic camera poses. Unlike traditional methods that assume static camera pose estimates, LivePose addresses the challenge of dynamic pose updates in online execution. This is particularly important for real-time applications on mobile devices, where simultaneous localization and mapping (SLAM) systems provide dynamic pose estimates that may be updated due to events like bundle adjustment and loop closure. The authors formalize the new task of dense online reconstruction from dynamically posed images and introduce a dataset called LivePose, featuring dynamic pose sequences for ScanNet, generated using bundle fusion. They propose a framework based on de-integration to adapt existing reconstruction systems to the dynamic pose setting. This involves de-integrating past views and reintegrating them with updated poses, ensuring that the reconstruction stays in agreement with the SLAM system. The authors select 3 recent reconstruction systems, including Deep Video MVS, Neural Recon, and Atlas, and apply the de-integration framework to each. They also propose a novel, nonlinear de-integration module based on deep learning to support online reconstruction for methods using learned, nonlinear update rules. The contributions of this work include formalizing the new task of dense online 3D reconstruction from dynamically posed RGB images, releasing the LivePose dataset, developing novel training and evaluation protocols, and proposing a recurrent de-integration module that learns to handle pose updates by removing stale scene content. The authors also discuss related work in dense visual SLAM, depth-based reconstruction, and implicit volumetric reconstruction, highlighting the limitations of traditional methods and the benefits of their proposed approach. They demonstrate the effectiveness of their de-integration approach through experiments, showing qualitative and quantitative improvement among 3 state-of-the-art systems with respect to key reconstruction metrics. The authors propose a novel approach to handling pose updates in online reconstruction systems, which is essential for real-time applications. They highlight the limitations of existing methods, including Atlas, Neural Recon, and VORTX, which either lack a mechanism for handling pose updates or require reconstructing from scratch at each time point, leading to significant computational costs. The problem statement is defined as computing an accurate online reconstruction of a scene given a sequence of images with continually updated camera pose estimates from an online SLAM system. The ground truth geometry at time t is obtained by fusing all depths before and up to t using the TSDF fusion operation. The proposed method involves a generalized pose update handling strategy, which is a generalization of the approach proposed by bundle fusion. The reconstruction state is updated by first de-integrating the bundle's contribution and then integrating it back with the corrected pose. This is achieved through 2 operators, F+ and F, which are implemented depending on the method applied. 3 classes of methods are discussed, including multi-view stereo, MVS, depth prediction, linear de-integration for neural features, and learned de-integration for neural features. For MVS, the authors adopt a TSDF voxel grid and use TSDF fusion to define the operators. For linear de-integration, they use a running average to integrate features into each voxel. For learned de-integration, they propose a novel, nonlinear de-integration step using a convolutional gated recurrent unit, GRU, to approximate the true de-integration function. The authors train their modified version of Neural Recon on the LivePose dataset with a time-dependent ground truth, which provides the necessary signal for learning the weights of the integration into integration networks. They also propose a pose update filtering mechanism to filter the pose stream from SLAM, emitting an update to the reconstruction system each time the current optimized poses have drifted significantly. Overall, the authors present a comprehensive approach to handling pose updates in online reconstruction systems, which is essential for real-time applications. Their proposed method addresses the limitations of existing methods and provides a novel solution for accurate online reconstruction. The proposed online 3D reconstruction framework incorporates dynamic SLAM pose updates, utilizing an intermediate layer to bridge the gap between SLAM and scene reconstruction. This layer employs a fragment generation system from Neural Recon, which subsamples keyframes from the SLAM pose stream. adding a new keyframe when the current camera pose differs from the previous one by at least 10 centimeters of translation or 15 degrees of rotation. This strategy enables real-time processing by reducing the total number of frames to be processed. When the sum of update distances over all views in a bundle crosses a threshold, the system produces 2 additional bundles. A de-integration bundle containing stale poses to be removed from the reconstruction and a reintegration bundle with new optimized poses. This approach ensures a tractable pose update frequency regardless of the SLAM implementation. The framework is evaluated on the ScanNet dataset using the LivePose data from LivePose, which estimates the full dynamic pose sequence for each scan. The results demonstrate the importance of de-integration in achieving coherent reconstructions. Without de-integration, pose updates can lead to significant discrepancies with respect to the ground truth reconstruction. Reintegrating with updated poses can recover missing geometry, but de-integration is necessary to remove stale scene content. The proposed method outperforms state-of-the-art methods in terms of accuracy, completeness, and latency. The results in Table 1 show that the proposed method achieves the best performance in terms of accuracy, completeness, and FS-score for all 3 base methods: Atlas, Neural Recon, and Deep Video MVS. The memory cost of the proposed method is also discussed, with the requirement of storing a depth image or feature map for each keyframe. However, the de-integration GRU in Neural Recon does not require storing a second feature volume, as it shares the scene state with the integration GRU. The LivePose dataset is introduced, which provides dynamic SLAM pose streams for a large number of RGB-D scans. The dataset is used to evaluate the proposed de-integration strategies, demonstrating their effectiveness in achieving coherent reconstructions in the presence of dynamic pose updates. The researchers present a novel approach to online monocular 3D reconstruction, focusing on handling pose update events from the SLAM system. They introduce a dataset of dynamic pose sequences, LivePose, which enables evaluation of reconstruction methods at intermediate time steps. The authors compare their bundle fusion pose estimates to official ground truth poses, achieving a mean absolute error of 5 cm in camera position and validating the accuracy of their pose data. The authors evaluate their solutions on ScanNet using dynamic pose estimates from LivePose, computing reconstruction metrics on the official testset. They compare their method to baselines, including Atlas, Deep Video MVS, and Neural Recon, demonstrating the impact of failing to respond to pose updates and the contribution of de-integration. The results show that their approach leads to the best outcome on all metrics, supporting the effectiveness of direct de-integration in handling pose updates. The authors also present an ablation study, characterizing their results and illustrating the importance of training with dynamic poses. They simulate perfect nonlinear de-integration performance by starting the reconstruction from scratch each time an update is received, providing an upper bound on the accuracy of the de-integration module. The results demonstrate that the learned de-integration achieves the fastest processing rate while maintaining comparable reconstruction quality. Furthermore, the authors investigate the effect of recomputing depth upon reintegration for Deep Video MVS, finding that the results are similar, indicating high internal pose consistency across updates. The authors conclude by highlighting the importance of handling pose updates in online monocular 3D reconstruction and introducing a novel de-integration module that enables pose update handling for methods using nonlinear view integration. This paper provides a comprehensive overview of the advancements in 3D scene reconstruction, particularly focusing on multi-view stereo, MVS, and visual SLAM, simultaneous localization and mapping, techniques. The authors discuss various approaches to enhance the accuracy and efficiency of these methods, including the use of deep learning models and transformer architectures. The paper begins by discussing the importance of 3D scene reconstruction in various fields such as robotics, augmented reality, and computer vision. It then delves into the challenges associated with MVS and visual SLAM, highlighting issues like scale ambiguity, viewpoint limitations, and computational complexity. To address these challenges, the authors propose the integration of transformer models in MVS and visual SLAM pipelines. They introduce a novel transformer-based architecture that can efficiently fuse information from multiple views and generate high-quality depth maps and 3D models. This approach leverages the strengths of transformers in processing sequential data and capturing long-range dependencies, which are essential for aligning and fusing multi-view images. The paper also discusses different techniques for improving the efficiency of MVS algorithms, such as using sparse feature points, optimizing cost volumes, and employing neural networks for depth estimation. Furthermore, it touches upon recent advancements in visual SLAM, including the development of direct and indirect methods, the role of deep learning in enhancing accuracy, and the importance of handling scale ambiguity and motion estimation. The authors emphasize the significance of benchmark datasets like ScanNet and 3D60 for evaluating the performance of MVS and visual SLAM algorithms. These datasets provide a platform for researchers to compare their methods and identify areas of improvement. In conclusion, this paper offers a detailed analysis of the current state-of-the-art in MVS and visual SLAM, emphasizing the potential benefits of incorporating transformer models in these tasks. By discussing various challenges, techniques, and evaluation metrics, the authors provide a comprehensive guide for researchers working on enhancing the efficiency and accuracy of 3D scene reconstruction algorithms.